So for the second session, we have Amin Karamlou telling us about polynomial comonads that do not distribute over distribution monads. He's from Oxford. Take it away.
Yeah, thanks. So this is joint work with Nihil, who is also in Polynomial. Okay, so I want to talk about monads and comonads, and in particular, when you can combine monads and comonads in a certain way. So I think maybe a lot of you are familiar with this, but monads and comonads, they're formulated as triples of things where you have an endofunctor, a unit, and a multiplication. These are natural transformations, and there are some coherence conditions that you have to satisfy. But perhaps more importantly for this talk, intuitively, what happens is that monads give you a model for effectful computation. So they model things like non-determinism, probabilities, certain quantum effects. And comonads allow you to reason about computation in a certain context. So in this case, we're going to deal with comonads that model prefixes of lists or nodes in a tree. And you can represent effectful computations as Kleistli morphisms of a monad. So these are morphisms where your codomain is decorated by the monad, and contextual computations are represented as co-Kleistli morphisms of the comonad. So your domain is decorated by the comonad. So a natural question arises here, and that's, what if we have computation that's both contextual and effectful? How can we combine these phenomena together? And as soon as you talk about this, you're sort of entering the realm of distributive laws between monads and comonads. Maybe some of you have come across this term before. Most often when it's used, it's referring to a distributive law between two monads, which is a way of giving you a composite monad on the same category. In this case, I'm interested in a distributive law of a comonad over a monad. So that's when you have something that goes from WM to MW. And it has to satisfy 4 axioms, so it has to interact well with the unit, co-unit, multiplication, and co-multiplication of the constructions involved. And something that's going to be important in this talk is that each of these axioms can actually be satisfied independently of the others. So you could just talk about satisfying the unit axiom, or just talk about satisfying the co-unit. And I'm going to say that there's a pointed law between, or maybe a pointed endofunctor law between W and M whenever just this unit axiom is satisfied. So why do we care about distributive laws existing? Well, whenever you have a distributive law, you can create what's known as a bi-Kleistli category. And that's a category where now both your domain and your codomain is decorated. So you have morphisms that are contextual and effective. That's the idea. And in fact, this can be seen as the Kleistli category of a version of M lifted to the co-Kleistli category of W, or equivalently as the co-Kleistli category of a lifted version of W on the Kleistli category of M. So distributive laws aren't always guaranteed to exist, and even when they do exist, it can be difficult to find them. And there's a result that's not published by Plotkin, but attributed to Plotkin, that shows that the power set monad doesn't distribute over the distribution monad. And then Dan Marza and Mike Azort have vastly generalized this to give us entire families of no-go theorems in the case of distributive laws between two monads. So in this work, we're going to derive some examples of no-go theorems, but for the case of comonad-monad distributive laws. And one of our main motivations for this was a question that arises from the game comonads literature. That's whether certain game comonads distribute over the quantum monad. In this case, the quantum monad actually is a graded monad, but it is still define suitable versions of the definition of distributive law in that setting. Okay, so I'll give you an outline for the rest of the talk. The idea is that we're going to start with a simple counterexample, which is choosing some naturality squares and doing some clever diagram chasing. And then progressively generalize that until we actually capture quite a large class of monads and comonads. Yeah. And then at the very end, I'm going to talk about how we can transfer the results to other categories. So for most of the talk, I'm going to be focused living sort of in the category of sets, but at the end, we'll talk about how you can generalize it to other categories as well. So the first no-go result that I'm going to talk about is between the power set monad and the prefix list comonad. So the power set monad just sends a set to all of its subsets. The unit is the singleton set, and multiplication takes a union of sets. The prefix list comonad sends a list to all the non-empty lists over that set. And co-unit gives you back the last element, and co-multiplication rather, sort of unravels and gives you the prefixes at each index. So you have a list of lists now. So our first results, and this is kind of the building block that we're going to use to get all of our results, is that there's no distributive law between these two things. And I'll just give you a quick sketch of the proof. There's a key lemma that's actually fairly involved to derive. I won't give you a proof of it, but it tells us that just to satisfy the unit axiom of the distributive law, if you satisfy that rather, then you have a unique natural transformation that's doing that. And what is this natural transformation doing? It's taking a list of sets and it's sort of keeping the shape of that same list and giving you all the sets where you pick out an element you sort of sample at different positions of the list. So once we have this, we can do a diagram chase of that co-multiplication axiom that I showed you. And if we chase around that diagram with this law that we now know is unique, or rather the unique candidate for the distributive law, we end up with two things that should be equal on this right-hand side not being equal. You can see here I have a set of cardinality 2, but down here I have a set of cardinality 4. And in fact, we haven't just showed that there's no comonad-monad distributive law. This is a stronger statement because we've showed that it's impossible to simultaneously satisfy the unit and co-multiplication axioms. Okay. So now I want to start generalizing this to cover more cases. The first thing I'm going to do is to generalize the comonad side of the construction. So for this, I'm going to be talking about container functors. And these are functors I'm going to write as this S triangle P shape. And the idea is that they have a set of shapes, and for each, the set of positions for each shape. And this construction induces an endofunctor. Yeah, I mean that I maybe won't go into too much of the details of exactly how it's constructed, but something that I know a lot of people are interested in polynomial functors here. So over sets, at least, containers and polynomial functors are equivalent. And then we can talk about directed containers. And these are containers where, in addition to shapes and position, you have a notion of the root of the structure and also a subshape at each position. And in fact, directed containers are precisely those containers that admit a comonad structure. So yeah, maybe I should have put a couple more references down here for directed containers, but that's sort of the paper that introduces these container functors. What are some examples of this? Well, really, a lot of things that pop up as data structures in computer science can be seen as examples of containers. So we've already seen this non-empty list or prefix list comonad as an example. Binary suffix trees are examples where you just, it's kind of like having a list, but now you're expanding in multiple directions if you have a tree. And then your co-unit is going to return the root. Your co-multiplication is going to return the subtree at each position. Yeah, I won't go over the pointed list. There's a pebble list comonad, and for those of you that know the pebbling comonad that's used in finite model theory, this is just a version of the pebbling comonad on the category of sets. So now your list also has an associated pebble at each position, and the co-multiplication and co-unit is similar to what we had before. And then for any set, this one's kind of important because I'll come back to it. We have the co-reader comonad for that set, where this is the product by S endofunctor, which has a single position for each shape. And then co-unit and co-multiplication are sort of the natural thing that you would come up with when you have such a simple structure. Okay. Then what we can do is we can extend this uniqueness argument that we had earlier to any container. At this point, I'm only talking about satisfying the unit law again. So actually, this result doesn't just hold for directed containers, it holds for all containers. And what it's saying is that there's a unique pointed law of containers over the power set monad, where you do the exact same thing that we were doing for the non-empty list. You sort of keep the shape of the original container, and then at each position, you sample from the sets that you had at that position. So this is the same counterexample I had as before, but then our insight now is going to be that this can really be phrased as a cardinality argument. So here we have a set of cardinality 2, like I said, here a set of cardinality 4. And by taking that idea seriously, we can say that for any directed container that has a shape which has like more than 2 positions in it, we can recreate this cardinality argument. And so we end up with this statement that says that for all of those containers, there's no distributive law over the power set monad. And then with a little bit of extra work on top of this, we can actually say that if a distributive law does exist, then we must really have some variant of the co-reader comonad. We have the co-reader comonad on some set. Okay, so that's how general we can make the comonads. We can also try to generalize the monads a bit. So I'm going to say this is not something that already existed. So this is a term we're introducing. I'm going to say that a monad is n uniform choice if the functor and unit part of it is n uniform choice. And then the definition is sort of, I've copied it directly from the paper. There's 3 or 4 things you have to satisfy. So firstly, you have to have a natural transformation from that monad into the power set. And then you have this n-ary, this is sort of an algebraic argument at this point. You have an n-ary term where you're taking the product of a bunch of identities, and this term has to be idempotent. So beta of a bunch of x's is the same thing as applying the unit. It has to be commutative, so it has to be invariant under various permutations. And then this support natural transformation has to, well, interact well with your term. These, I admit, if you haven't seen what our argument is, these might seem a bit arbitrary. The reason that we've chosen these things is because they're precisely the sort of conditions that allow us to perform this uniqueness argument. So that the uniqueness argument relies on, we call it the swap collapse relabel argument, and it relies on having these sorts of terms. Okay, so but that's a bit of a contrived definition maybe. So do we have interesting examples that fall into this class of monads? And the answer is yes. We've already seen the power set monad. Another thing that falls into this class is the distribution monad, where you're sending a set to the set of all probability distributions with finite supports over that set. Another example is the filter monad, which I won't really give you a definition of, but it is, you can see that these things maybe look, at least on the surface, quite different. So it does seem to cover a large class of monads, this definition. And in fact, it covers the distribution monad on different semi-rings as well. Not the distribution monad on all semi-rings, because we need conditions on the semi-ring. For instance, it has to be zero-sum free, but it does cover a large class of distribution monads. Right. So we can again come up with a sort of uniqueness argument. This time we're not saying that the natural transformation satisfying unit axiom is completely unique. We're going to say it's, quote, unique up to supports. So that means that if I perform this support transformation on both sides, I end up with some sets, and those sets are going to be equal. And then again, we can say that we're looking at the class of uniform choice monads where n is greater than or equal to 2. And we generalize our earlier no-go theorem. So now we can say that any comonad that's a directed container satisfying that cardinality constraint, and any monad that satisfies this cardinality constraint don't have a distributive law. Okay. So this is what we've done in the category of sets, but like I mentioned, the original motivation was looking at game comonads and this quantum monad, and those things actually live in the category of relational structures or in the category of graphs. So what I would like to do now is argue that we can generalize our results to these other categories, or extend them rather. And yeah, one motivation for this is because comonads on the category of graphs, or more generally on the category of relational structures, have been shown to have very strong links with techniques in computer science that are used for studying relaxations of things like graph homomorphism and graph isomorphism. And these are tools that are very useful in fields like finite model theory and constraint satisfaction. So it would be interesting to see if we can come up with a way of combining these homonadic and monadic relaxations that pop up in these settings. Okay, so I have two examples of comonads on the category of graphs here. One is the Ehrenford-Frisé comonad. This captures Ehrenford-Frisé games for those of you that know what those are. And it's very similar to the non-empty list comonad that I had defined earlier. In fact, its action on the underlying universe of the graph is exactly the same action as the non-empty list comonad. And then it also has something that it does to edges, because we're working with graphs now. So then there's another monad, which I've called the BLP monad. And this captures something known as the basic linear programming relaxation of constraint satisfaction or graph homomorphism. And again, its action on the underlying universe of the graph is exactly the same as the power set. So clearly there's some very strong similarities between the Ehrenford-Frisé comonad and the non-empty list comonad, and between the BLP monad and the power set monad. And so intuitively, what we would like to argue is that if there's no distributive law at the level of sets between non-empty lists and the power set, then there's certainly no distributive law when you add more structure and you're dealing with more complicated constructions. And in order to formalize this, we're going to use what we call transfer theorems. So there's sort of two parts to the theorems. And they generalize an earlier result of Mains and Maury. They're quite verbose, I'll just warn you, but they're verbose because it's the natural thing that you would come up with when you just try to categorify this intuitive argument. So I'll just I'll try to get the intuition across for what's going on. So the first transfer theorem, there's some assumptions that I'm going to make. I'm going to say I have two categories, C and D, and comonads. So I have these different fonts to represent the categories living in different the comonads living in different categories. So I have a comonad in D, a comonad in C, a monad in D, and a monad in C. And then I need to say that the comonads living in different categories are related reasonably, the monads are related reasonably. So I'm going to say that if you assume that there's a co-Kleistley law between the comonads, that's a sort of a distributive law where you satisfy the co-units and co-multiplication, and a Kleistley law between the monads. And then you have pairs of natural transformation, one living in the category D and one living in the category C, that satisfy an additional coherence, that's a Yang-Baxter style equation. Then I can say that if one of these natural transformations is a distributive law between the comonad and the monad living, say, on the category D, then the other one has to be a natural transfer, has to be a distributive law between the comonad and monad living in the category C. And then the second part of the transfer theorem gives you conditions. It's a similar sort of thing, but what it's doing is giving you conditions that guarantee that this Yang-Baxter equation is satisfied. And for that, we're going to, for instance, make use of the fact that sets are co-reflective subcategory of graphs. So that's the intuitive picture of what's going on. And in fact, both of these theorems have nice string diagrammy proofs. So for instance, if I wanted to prove that the unit axiom is satisfied in the first theorem, the string diagrammatic proof would look something like this, where it's a combination of the fact that we know one of the things already is a distributive law, so we're going to use the unit axiom of that distributive law. And then over here, for instance, I'm using the Yang-Baxter equation to swap this triangle around. Yeah. How much time do I have? Okay. So the most general no-go theorem that we've managed to come up with in this work says that we have a class of monads on a category D that have an isomorphic Kleistley law into a monad that's in our earlier class. And likewise, some comonad that has a isomorphic co-Kleistley law into a comonad in our earlier class. Then there's no distributive law between these things. And so for instance, a straightforward corollary of that, we can say that there's no distributive law of this Ehrenford-Fraisier comonad over the BLP monad. That's actually the end of the work that's been done. I thought if I had some time, I would just speak about something that seems reasonable and might hold, which is a way of partially overcoming these things, so you get some form of composition back. And the idea here is that many of the functors that I've been talking about have a natural notion of grading that comes with them. So for instance, this non-empty list functor, you could imagine that I restrict it to all the lists that are up to size k. And this will allow us to define a graded version of that comonad, graded over the natural numbers under multiplication, say. And it seems like if you now try to come up with a distributive law of this graded comonad over the power set monad, you don't run into the same issues as before. Maybe I have just about enough time to explain what I mean by that. So if I go back to this diagram I had at the beginning of the talk, You see this? We saw that the co-multiplication really is the thing that breaks. But if I had to grade my co-multiplication, it would look something like this. And yeah. So there's this finer sort of way of dealing with the resources, the length of the list in this picture. And what that means actually is that the natural transformation that you're applying here does not have to be exactly the same thing that you're applying here. So again, you can apply different natural transformations at different grades. And so you wouldn't run into this cardinality issue basically, because yeah, this issue here wouldn't arise because you would have a different co-multiplication, and in fact you'd end up with down here, you'd end up with precisely the same set that you had up there. So this seems to be a way of overcoming the lack of existence of distributive law, but of course you're working in a slightly different category. And your co-Kleisli morphisms are going to be different. Okay, I think that's all I have.
Yeah, any questions?
Thanks for the talk. So you talked about how these various no-go theorems, and it's like a common theme. Whenever anybody gives a talk about the no-go theorems, somebody asks a question. What about the go theorem? So,
Yeah. Well, that's why I had this thing at the end.
They have a suspicion that some of these problems might be solved just you are able to weaken the structures, maybe apply grading. Talk about grading, maybe something to do with higher categories, blah blah blah, yada yada. Have these things been explored? Have you thought about this grading? Have you thought about maybe a weaker version of what a distributive law might look like?
Yeah, I mean, so there is a thing called a weak distributive law in the case of two monads, and that's where you drop one of your unit axioms. And in fact, Alexander Gois has done a lot of work on this and others have done a lot of work on this where, for instance, for the probability versus non-determinism case, which is Plotkin's example, you can actually come up with a composite monad when you satisfy 3 out of the 4 axioms. This sort of grading seems to be another way of overcoming that same barrier. So these things have been explored. We tried looking at weak distributive laws for our bi-Kleisli case as well. It's a bit harder because for us, the thing that breaks is co-multiplication. And co-multiplication is actually quite important to the structure of the comonads that we're interested in. Yeah.
The notion of weak multiplication, weak comonads, weak comonads.
I think you should get some sort of category out, but yeah. It's yeah.
Sorry, just to confirm, did you say that in the pseudo case, the no-go theorems don't hold that there are actually distributive laws, where in the one-dimensional case that is not?
Sorry, what do you mean by the pseudo case?
So in the two-dimensional case where you're dealing with pseudo-monads and pseudo-distributive laws, where you have distributivity up to isomorphism, is part of what you said that in that setting, you are actually able to get distributive laws well.
I don't actually know what pseudomonads are, but that's not what I.
So
Yeah.
weak distributive law should be like a distributive law for a pseudo monad.
Yeah, maybe. I don't know it in that terminology, so I can't say for sure.
Perhaps we'll talk about
Yes.
Few more,
So, the Nonad is component. You can define, well, you can define it on item. Then it ends up being the monad, you will need your base character description. So you start with a class that has something to do with the preserving. Is there like similar program preserving thing?
I guess we haven't thought about it in that term, but it's a good question. Yeah. Not immediately.
maybe take one more question because we're running into the break. Cool.
Like I was wondering if you thought of this could be regarded as a street of loss between like bimodules of monads, which, for example, if you look at like spans of sets, this is the street of law between set and set up, but not as monads. So bimodules of monads up to the isomorphism, so you can identify the kind of shift the structure that is the obstruction.
I know there's some work on this that you and others have done, but I'm not super familiar. So yeah, I don't, because we're dealing with very concrete examples here, right? Because we're motivated by these games and CSP relaxation. So it's, but maybe there is a link.
All right, I would take other questions to the speaker offline, and let's thank him again.